Welcome to ScienceCover.com. Today we're going to be looking at electrical efficiency, and we look at how to calculate the efficiency, what is meant by the efficiency, and how we can rearrange the equation to complete calculations. First, pause the video and complete the Do Now task. Let's check our answers to the Do Now task. Explain what is meant by this diagram and where it can be found. Well, this is a sticker which tells consumers how electrically efficient a device is. So the A triple star rating means that the product is very energy efficient. That means that most of the energy that it goes into it is being used for the purpose for which the device is created. Whereas a rating of D or C can be considered not very efficient, because this means a lot of the energy that's being put into the device gets wasted. Let's now look at what we mean by the term efficiency. Efficiency is a measure of how much energy used by an object is turned into useful forms of energy. So an efficient device turns most of the energy that it uses into what it needs. For instance, this toaster turns most of the electrical energy that goes into it into heat. It will still waste some energy as light and sound, but if it's an efficient toaster, most of that energy will become heat, because that is our useful energy type. Inefficient devices convert energy to unneeded forms of energy. So this old-fashioned light bulb is considered inefficient as it turns 95% of the electrical energy that goes into it into heat. In reality, it's more of a heat bulb than a light bulb. Efficiency is usually stated as a decimal number. This means that 1 would be a perfectly efficient device, something that uses all of the energy going into it for what it was supposed to use it for, and 0 would be perfectly inefficient, so all of the energy going into it and none of it gets used for what it's supposed to be used for. We can calculate the efficiency of a device by looking at the useful power that it produces and dividing this by the total power that was going into the device. And since the useful power is measured in watts and the total power is measured in watts, efficiency doesn't have a unit. Now pause the video and attempt task 1. Let's check the answers to task 1. The first question, we had to fill in the blanks. So efficiency is a measure of how much energy is turned into useful energy by a device. Efficiency is usually stated as a decimal number. 1 is considered perfectly efficient and 0 is considered perfectly inefficient. All non-useful energy created is classed as waste. So the missing words were energy, useful, decimal, efficient, and waste. Question 2 is to complete the equation for efficiency. So the efficiency is the useful power divided by the total power. Let's now have a look at some examples how we can calculate efficiency using the equation. So we've said earlier on that we expect efficiency to be a number between 1 and 0, and we can calculate this number by dividing the useful power by the total power. Example 1. How efficient is a light bulb that uses 50 watts of power and wastes 46 as heat? Well, the first thing to do is to calculate the useful power. So we're putting in 50 and we're wasting 46 as heat. So that must mean that 4 watts is used as useful power. So I can now place this into the equation. The useful power divided by the total power will be 4 divided by 50, which gives me efficiency of 0.08. Example 2. The computer uses an average of 180 watts of power over the course of an hour. If 20 watts was lost as heat, how efficient is the computer? Well, first let's work the useful power out. So we're starting with 180 watts and we lost 20 as heat. So we must have 160 watts going as useful power. So I can place 160 as useful power and divide it by 180, the total power. And this gives me 0.89. Now pause the video and attempt task 2. Let's check our answers to task 2. Question 1. A 120 watt light bulb is switched on overnight. If 6 watts of this becomes light, how efficient is the light bulb? Well, we can calculate the efficiency using the useful power divided by the total power. And we're told that 6 watts has become light, and we were told that it was a 120 watt light bulb. So you can do 6 divided by 120, which gives us 0.05 as an efficiency. Question 2. A lightsaber requires 200 watts of power to function correctly. If 80 watts is turned to light, how efficient is the lightsaber? Well, again, we can do useful power divided by total power. So the useful power is 80 watts in this case, and the total power was 200. So 80 divided by 200 gives us 0.4. A coffee machine uses 140 watts of power. If 70 watts is wasted as heat, how efficient is the coffee machine? Well, first let's calculate the useful power. We're putting in 140 watts and 70 gets wasted as heat. So this must mean that the other 70 watts is used on useful power. So now we can work out the efficiency by doing useful power divided by the total power. So this is 70 divided by 140, which gives us 0.5. Question 4. A footballer is running on a treadmill. His body is burning 2 watts. If 1.2 watts is being turned into kinetic energy, how efficient is the footballer's body? Well, we're given the useful power here as 1.2 watts, and he's burning 2 watts as his total power. So we can do 1.2 divided by 2, which gives us 0.6. For question 5, a kettle uses 200 joules of energy in 50 seconds. In this time, 175 joules has become heat. How much energy was wasted by the kettle? Well, the useful energy from the kettle is the heat, and we know that 175 joules of our 200 has become heat, so it must mean that 25 joules gets wasted. What is the power use of the kettle? Well, we're using 200 joules in 50 seconds. To find the power, which is the energy per second, we just divide the energy by the time. So it's 200 divided by 50, that gives us 4 watts. How much heat energy does the kettle produce each second? Well, this is working out the power of the heat energy. So again, its power is energy divided by time. So that's 175 joules in 50 seconds. So 175 divided by 50 gives us 3.5 watts, which means that you make 3.5 joules per second. How efficient is the kettle? Well, to work that out, we can do the useful power divided by the total power. So that's 3.5 divided by 4, which gives us 0.875. Now let's look at how to rearrange the equation. We can place the efficiency equation into an equation triangle with useful power at the top and efficiency and total power at the bottom. Now we can work out how to rearrange the equation by covering up what we're looking for. So if we are asked to find the useful power, you cover up useful power, it tells you it's the efficiency multiplied by the total power. If we're asked to find the efficiency, cover up efficiency, it tells us it's the useful power divided by the total power. If we're asked to find the total power, then you cover up the total power, and we're left with useful power divided by efficiency. So let's see if we can use these three rearranged equations in calculations. Example 1. A toaster has an efficiency of 0.4. If it runs from a power of 20 watts, how much power gets converted into heat? So we want the useful power. So let's cover up useful power, and we're left with efficiency multiplied by power. So the useful power is efficiency multiplied by power. Next, I can substitute in the two values I'm given for the words in the equation. So I've got an efficiency of 0.4, and my total power is 20 watts. 0.4 times 20 gives me 8, so the useful power must be 8 watts. Example 2. A microwave oven runs from a 200 watt source and converts 180 watts to heat. How efficient is the microwave? Well, in this case I want the efficiency, so cover up the efficiency, and we're given the useful power divided by the total power. Substitute in the two numbers that I'm given in the question, so 180 being the useful power and 200 being the total power. And 180 divided by 200 gives me 0.9 as an efficiency. Example 3. A speaker outputs 3 joules of sound energy each second. If the speaker has an efficiency of 0.6, then what was the total power into the speaker? So the useful power in this case is going to be the amount of energy per second, and we're told that it outputs 3 joules of energy each second. So I can just take 3 watts as the useful power. Now to find the total power, I'm going to have to do the useful power divided by the efficiency. So if I use my 3 watts as the useful power, then I can divide it by 0.6 as the efficiency. 3 divided by 0.6 gives me 5, so the total power must be 5 watts. Now pause the video and complete task 3. Let's check our answers to task 3. Number 1, a light bulb gives out 15 watts of light. If the bulb has an efficiency of 0.05, then what was the power of the source of the electricity? So the total power is the useful power divided by the efficiency. So that's 15 divided by 0.05, which gives us 300 watts. A drinks dispenser uses 12 watts power source. If it has an efficiency of 0.75, how much power is used to dispense a drink? Well, the useful power is the efficiency multiplied by the total power. So that's 0.75 multiplied by 12, which gives us 9 watts. A fridge runs off a 20 watt power source. If the fridge is considered to have an efficiency of 0.9, what is the power used to keep the air cool? So the useful power is the efficiency times by the total power. So that is 0.9 times by 20, which gives us 18 watts. Question 4. An electrical car battery has an efficiency of 0.6. If 50 watts of power is used to move the vehicle, how much power did the car battery produce? So we're after the total power. So this is the useful power divided by the efficiency. So that's 50 divided by 0.6, which gives me 83.3 watts. A rocket engine fires and produces 300 watts of thrust to raise a rocket off the ground. If the rocket is burning fuel at a rate of 400 watts, how efficient is the rocket? Well, the efficiency is the useful power divided by the total, so that's 300 watts divided by 400 watts, which is 0.75. How much energy is being wasted each second? Well, we can do 400 watts minus 300 watts, which gives us 100 watts of power being wasted, and that means that there's 100 joules per second being wasted. What happened to the wasted energy? It gets lost to the surroundings as heat. Question 6. A fan is plugged into the mains. A fan uses 30 joules of energy each minute and has an efficiency of 0.8. What is the total power used by the fan? Well, the power is the energy divided by the time. So this is 30 joules of energy divided by 60 seconds, which gives us 0.5 watts. What is the useful power from the fan? Well, the useful power is efficiency times by total power. So that's 0.8 times by 0.5, which gives me 0.4 watts. How much energy is wasted each second by the fan? Well, I can take the 0.4 watts from 0.5 watts, which gives me 0.1 watts. So that's 0.1 joules per second.